Okay, again, the definitions that we've gone over in the past class, I'm still finishing the videos. I had a lot of work come in all of a sudden. I've been a little busy. It's right under here, under the tutorial section, and then general software, and then the Grasshopper folder. You'll have all the definitions that we worked through in class. So in the event that you can't follow along, because I do move pretty fast with these, you can pick these up and use them as I go. So you'll be a little bit ahead of me, and you can play around with them. So basically, what I want to go over today is doing math and lofting surfaces and all those things in Grasshopper. So here I have something that's probably way beyond anything you'll ever encounter in your career at IIT, but what it is the attractor script taken to like the nth dimension. So I have a series of points, and we're not going to do this, but basically it's nice to know that I can take my Grasshopper model here, and it's going to crash on me. But basically I can script in a math formula, and so if I have calculus class, right, as long as I get everything down to its derivative and into an XYZ function, I can generate and have Grasshopper do all my calculations for me. So it's pretty much like a calculator. It has all the things necessary for you to use, and I'm going to end up crashing this guy. So, and I had to actually custom script this piece in. So if you're ever interested, you can just always contact me, and we can work through it with you for anything you may have. But I want to kind of dumb it down from here and start from like just a basic sine wave. So I'm going to go ahead and just kill my task here. There we go. All right, so I'll fire up Grasshopper. And the first thing is anytime we're going to build a surface, right, and especially in architecture, if we're going to end up building that surface, we're going to end up building that surface, you're going to want to have some way of calculating, one, the sizing of the members, the placement of the members, and for structural purposes, you really want to have it derived from, hopefully, from a mathematical formula. Now, with the way of the computers and the way of the world now, pretty much you can spit on a page and call it architecture and build it if you have the amount of money. But you can always save money in the process if you begin at a starting point. And really, math is a great starting point for any type of design work, for that matter. And then if we're going to do like a skin on a building, we're going to pattern that surface. You think of just the rectilinear buildings; those are just building patterns. They're just surfaces that are patterned. So that's the same thing we're going to take today and kind of work on that premise. So what I can do is I'm going to open and show you what we'll do here first. So let me check first number 1. Okay, so when I look at the first script here, and it's a little dirty here for now. Basically, what I've done is I've taken and scripted in a sine wave, and then I've scripted in a cosine wave, and then I just loft a surface in between it. And I can show you that here. So I take my pipe command, turn that off, and if I look at my lofted surface, and then I subdivide that surface into a series of panels. So it's kind of like taking the wireframe out of it, and then making a paneled surface from that. What's nice about this is it's the same way as saying that if I have a plane or any kind of surface in Rhino, and I have my ISO curves there. My ISO curves, I know that I can adjust the density through the properties, and that becomes my wireframe. So that's essentially what we're doing today. We're going to do first with this surface. We're going to divide that out. But what's nice about doing it the Grasshopper way is I'm able to, with the ISO curve density as it's shown here, I can't change the distance in between these. It pretty much arbitrarily divides that surface into even increments for me. I have no way of saying, distinguishing my X versus my Y dimension. Whereas by doing it the Grasshopper way, I'm actually able to adjust how many I have in the Z direction or the V direction, and so on and so forth. So I have global control over that ISO curve surface. And then I can make a diagrid out of it, or any type of structure for that matter. Or I can even place circles inside that. We'll do something next week. I'll give you a script that actually makes the attractor points work on this as an opening panel. But that's the idea. So, and it really all starts with just doing simple math. So we're going to start right here. So I'm going to keep this open because I'm going to have to go back on my notes. I've been doing a lot lately here. So I got to remember. So I'm just going to copy my function over there. I'm going to go new document. Take that off. All right, I'm going to paste that in so I have my references. So how I'm going to tackle this is it's basically a formula. And from the thing I showed first with the Lorentz attractor was actually scripted in. So I wrote the script, and it's in VB. So Rhino reads VB in C# if you're interested. And I can input my own math functions. Now there also are every type of explicit thing. So if you wanted to do something by hand, you absolutely could do it by hand. It just takes you a little longer. I'm working with a math student. They got a formula that's probably like this long in 12-point font. To do that by hand was silly. So we scripted it out. But I basically want to set up variables where I have my variables here. So I need one for time. So this is the angular frequency. So the sine wave's always plotted over time, right? So that's the t. So I need a difference in time, and I need a division in time. So I also need a y value. Y value is going to be the points that get pumped out, and then we'll plot them over time. So t is almost like our x value. So I'm going to do a phi, an omega, an amplitude, 2 t's, and that should give me my variable. So anytime we're doing an input for math, it's going to be a variable. It's going to be a number slider or whatever it may be. So to do that, I do a number slider. And I'm going to copy that. I need 1, 2, 3, 4, 5. I need 5 of them. I'm going to edit that, and I'm going to call 1A. Right-click. The next one is going to be omega. The next one is going to be phi. The next one is going to be t. And then one is going to be t n. So we'll have time in x value, just so you know it corresponds to the x. And then the other one's going to be time interval. So we'll also tell it how many times, how fine of a resolution we want for our line over the plot time. Okay, and I think I want to actually increase my maximum range on these, so I'll go up to 12 on each one. I may or may not need to go to 12. At this point, I'm not sure, and I'm assuming that I'm not sure, so I'm just going to give myself enough room to play with it. Okay. All right. So then I need to begin developing my formula. So my formula here is omega times t plus phi. So the first part is I know that I need to have a set of time derived from this. So I need a range value. And let me just make sure I'm on the right set here. Yeah. Okay. Okay, so, and also because if we remember in physics that whenever we look at a sine wave, it's just a circle with a point, and that point spins as the circle moves along the x direction, and that's how we get the sine wave or the cosine wave. So anything that's angular like that, we're going to need to times by pi. So the first part is I'm just going to type in pi, right, and then I'm going to crank that up to 10, and maybe I'm going to make this an actual interval, so just make this a 10, so I don't have to adjust it too much. And I'm going to times that by pi. So anytime I use the pi function, whatever I plug that into, it's going to multiply that by pi. And then the next part is I'm going to set up a range of values. So that range is going to give me how far in time am I going, and that's where my interval comes in. So I take my domain, and my domain is going to be whatever 10 times pi was. And if I look at my panel output, so I type in panel into Grasshopper, and that allows me to look at what I'm outputting. So basically, it's just giving me an even number of intervals across whatever this maximum value is, and I'm going to start at 0. Now, I could fine-tune this and say that maybe I want to go negative or positive, and I can construct my own domain from this. But since I'm always going to be working in a positive direction, I don't need to do that. And then my steps. So my steps is going to give me how many. So from 0 to 10 times pi, how many divisions of that do I want? And so in this case, I'm going to edit this, and I'm going to give it an integer. And maybe I want, 100 different intervals. All right, so I crank that up to 100. And you can see now I have values for x that correspond evenly. So it divides that basically out evenly into steps. Okay, so that gives me my full factor of t. So then I need to take my full factor of t, and it says times that by omega. So omega is just a variable, and it's an input slider. So I see that here. And I'm going to type in multiplication. I'm going to multiply omega times that value. That came from my range. And then I want to add phi to my multiplication result. So that whole set gives me this omega times t plus phi function. So I wrap it. I do my same way I would plug this into a calculator by hand is I construct the Grasshopper function to be the same way. Okay. Then I take that whole set. So the end result from the addition is really just that whole assembly now. And I need to take that times sine. So I take a multiply times sine. So I can just type in sine as my value. And then sine, let me just double check that I'm doing that right here. Yep. That's my addition. Yep. Then I multiply that. So that last part of my sine wave gets multiplied by whatever my amplitude may be. So I multiply that. So it's A times B. And then that gives me a range of x values now to correspond with or it gives me a range of y values. So I basically just now solve for y. So this is my y values, right? Because we're always solving for the function of y is t, right? So then my x values, remember we defined when we made our range. So those are my x values. So I can take my range, plug that into a panel, and these are my x values. And then I need to just construct a point from the y coordinate to the x coordinate. And you'll see there's my sine wave slowly mapped out. So I would adjust now how I look at that. So there's my sine wave. Right, now I can adjust the phase angle, the frequency of that. Time interval is going to be how long it is. And then you'll see that those points now, that's how I adjust the fidelity of my sine wave. The last part is right now, because we have so many points, I can begin to map out what it looks like. Take omega down. Something a little looser, right? If I get to a point like this, it's hard to map out what that looks like. So I actually need a curve now to generate that from. So the last part is to make a curve from a set of points. In Grasshopper, it's just interpolate data, or excuse me, interpolate, just the straight interpolate function. And my vertices are those points. And that's my sine wave. So you'll see, if I don't have enough points plotted, it's not going to give me a nice smooth curve. Maybe I don't want that. Maybe that's not what I want. But for this, I really want to, the more points I have, the finer and more accurate that curve becomes. Okay. Now, if I wanted to do a cosine, the cosine, tangent, and sine work the same exact way. So if I'm going to actually bring this down, yeah, I'll leave it at the top. If I wanted to do a cosine, leave that as my domain set. This all belongs to sine. I'm going to copy this up. And now my cosine value is going to be a multiplication result of the same function, but instead of doing sine, I'm going to replace sine out with cosine. So what I can do is I need to map my cosine value to my multiplication, and then I'm taking A, and then I'm taking the addition result into my cosine, and my cosine gets multiplied by A, and then those become my new y values. And then I can plot a series of points from that. Oops. Y, 2x. There's my cosine. Now, for sake of ease, I set this up so that way that these variables are independent of each other. And I believe my amplitude may have, well, not adjusting the cosine there. Well, okay. All right. Now I'll make a line out of that cosine. So I have two lines to work with. Okay, now I can build a surface from both of those segments. But before we do that, we kind of went through a long way of handling that. So that when you get more advanced, and I show you that so you can kind of track this out for yourself, because sometimes people aren't good at scripting. The easy way to do this, right, is I have these variables, is I can also just write an explicit expression. So I have my expression here, which is A times sine and the omega t plus phi, right? Well, we'll leave it at that. Because yeah, we can do that because this becomes t. Is what I can do is I can type in the expression script. So if I go to the function, so it's under the mass set, and I go to function evaluate. So basically I have my expression, so that would be what I type into my panel. And that's going to be A times the sine of omega times t and then that's plus phi. And then I plug that into there. Now it's going to throw an error and it's going to tell me parameter x doesn't have a name in parameter y. So what I can do is I can now add in my own variables here as inputs. So I'll go ahead and I can change the name of this to be omega or A. And then I need one for omega. And then I can add one here. And I need one for phi. I add another one. I need one for t. So then I know t is here. So everything I did up to the multiplication here, or up to my range, is going to be my time and interval here. So that calculates t. So I can plug that into my t value. And then I'm going to copy my phi, a, and omega down. There we go. So that also then solves for y. And it's a little nicer. It cleans up the script a little bit. I could even script this as a function. So this compared to all of this, right? So when we're doing giant functions, you know, it's always nice to think ahead a little bit on how we're going to map this out. Okay. So I'll group this together as option 1. This is option 2. I'll work under option 2 for this. Right, and then I don't even need to bother with the sign. And then I can do my panel, and I see that my range of x values, or my y values, are here, and they should match pretty close. They should be the same for those values. I'll double check it. There. And then my x values, panel. So we'll right click, call this y, call this one x. And again, my range was my x value. And I can construct a point from that. And I have basically the same thing, but it just took less steps to make. There we go. Matches the same exact one. So that's proof that it does work the same way. So I'm going to go ahead and hide those functions there. And we'll do the same thing. And we'll do the same thing with a cosine function. So basically I just take that same thing, and now when I want to change that, instead of having to go and repath and remap everything, I can just edit this to be now my cosine. And you'll see that somewhere, because I got so messed up with where I was, you'll see that this cosine value now is the accurate one. The other one, when I was pulling the slider, I got something plugged in goofy somewhere. So this is a good way to manage everything, is by simplifying the problem. Okay. So there we go. And all I had to do for this one was, for here I had to literally reconstruct the whole thing. Here all I had to do was change three letters. So if you want to see what a tangent looks like, we can do that as well. There's my tangent function. Right. So this probably would have been nice first year when you did analytic trig. You could have just did all your homework in the computer. Do you guys still take that? Do you still have to do analytic geometry for math?
First year.
You don't do that till your third year?
Well, first year.
First year, yeah, first year. That's what I thought. I was like, man, you guys got it easy. Okay, so anyways, so that's simple math, right? You can go as far as you want to take it. Like I said, I can show you the function here that we're working with. So that thing is like that long. So to do that the long way is a pain in the butt. So I just do it here. Okay, so now I want to actually go back to Grasshopper here, and we're going to make a surface from these curves. Now I won't use the tangent because the tangent obviously is a min and max form. It's not going to do a nice line for me. I mean, I could. If I connect the line, you can see what each one looks like. Again, the line is interpolate. There. Right. So you can see how nasty the tangent gets if you don't handle it correctly. So we'll just definitely hide all that. Okay, and I'll hide my point data. All right.